Hello guys, this is actually the continuation of the previous talk where actually we have calculated this Gaussian integrations x0 minus x square that is actually root over pi. And how did we do that? Actually probably you remember that we define it as the I, and then we multiplied I into I, and then we write this I in terms of x as well as y, right? And then it will be x square y square, right? This is the way. And then we say that this x square plus y square in polar coordinate is actually r square, okay? And then transforming this Cartesian coordinate to the polar coordinate, we can calculate this I square, sorry, and from there we can get this I, okay? And here actually I want to show you that not only that means it is necessary that we transform in a two-dimensional coordinate system, we can transform it a n-dimensional coordinate system, right? That means we can write I to the power n, and I to the power n, so there is a generalized coordinate. That means if there is n-dimensional coordinate, then there will be n independent variables. That means x1, x2, x3 and up to xn, okay? So in two-dimensional our x1 was x, x2 was y, and if we the three-dimensional space we actually say x, y and z, okay? That is the case. And in n-dimensional actually we express these variables at x1, x2, x3 to xn, okay? And equivalently, if we transform this n-dimensional Cartesian coordinate to a n-dimensional polar coordinate, then the distance, the definition of the distance, that is actually the same. That means x1 square plus x2 square up to xn square, that will be r square, no doubt about that, okay? That is the same thing. So in the polar coordinate there will be r, and there will be n minus 1 other variables which are actually angle variables. So there will be only one radial, that means variables for radial distance, and other is the for angular part, okay? So in three-dimensional it was theta and phi, and then for four-dimensional, five-dimensional and anything else, we can write it actually theta 1, theta 2, theta 3 to theta n minus 1, okay? So that's how the actually a polar coordinate can be defined in dimensional space, okay? The visualization may be little bit difficult, or to draw it in a whiteboard it will be difficult, but that is the abstract way of this is the abstract thing which we can actually extend to n-dimensional coordinate systems and express it in that way, okay? So all this that information is there, and so we can use it. And so we write this I to the power n as actually e to the power minus infinity to plus infinity dx1 to plus infinity dx2 to minus infinity to plus infinity dxn, and here it is actually e to the power minus x1 square, x2 square up to summation xn square, okay? I hope you understand this, right? That is the thing. Okay, so again, as I said, that this summation is actually r square. Okay, so the radial distance in the n-dimensional space, and then there will be change in this volume element, that is actually dx1, dx2 up to multiplication of dxn, and this is actually given by d theta 1, d theta 2 to d theta n minus 1, and there will be radial a radial element which is dr, but they will be associated with another radial part which is actually r to the power n minus 1. Okay, so how do you get that? Actually, that means this is that means you can understand easily that when if you have a two-dimensional space, this is actually r dr, right? The radial part is r dr. If the three-dimensional, this is r square dr, right? This is the case. Because that means two-dimensional space, this is actually just a line r. If this is three-dimensional, this will be a surface, and n-dimensional we can say it is a hyperface. Okay, so this is the area of a hyperface, and then we we can actually get this that means this volume element, right? So I think you understand that means for n-dimensional, this radial part will be r to the power n minus 1 dr. Okay, that is the case. So what we can do, we can then transform this to a polar coordinate and write it in terms of a r and theta. Okay, and so there will be n minus 1 theta integral d theta 1 d theta 2 to d theta n minus 1, and there will be a r part 0 to infinity at r part r to the power n minus 1 e to the power minus r square, right? I hope you all understand this actually. Okay, now as you may know that this theta and r all are independent, right? All are independent variables, so because there's a coordinate system, so they are independent, and so we can do this integration of r. I hope you can do this integration of r. So how you can do that? You can do that means again we can say this r square equals to u, so r equals to actually u to the power half. Okay, and so here actually this is 2y r dr equals to okay, 2y equals to du. Okay, I hope you understand this. So we can replace it there. So we can replace it here from this term. So what we get? Just write this portion, okay, and write it here that r square is u. R square is u. Okay, so we replace this. Okay, and let's call it actually d some omega. Okay, omega n minus 1 the whole integrations as this, and then we can say this so this is actually half du. Okay, because this one they said because this is 2r dr du, so r is actually what you can say, that is r n minus 2, because you say r dr twice rdr equals to du. So twice rdr equals to du, and so you take one from there, so it will be rn minus 2 e to the power minus r square, right? So now we replace this r with u, and then so if you replace this actually, so it will be u to the power half, right? U to the power half, and here it is actually e to the power minus u. Okay, so let me just write it. Okay, let me write it here. Then what is it? This is half du e to the power n minus 2 minus 1. I have to get it e to the power minus u. Okay, 0 to infinity. Okay, so what happens? Let me just remove this portion. And then we can get this integration. I think you now get it. That means what is this value? This is again, we can use this gamma function, right? Here we have to use this gamma function. So what is this gamma? Gamma p equals to 0 to infinity dx x to the power p minus 1 e to the power minus x. I hope actually you all know that. Actually I discussed it in in my past video, that is the integration 1 for the generalized Gaussian integral. So here actually I define what is this, and this is the Gaussian integration. So okay, sorry, this is the gamma function, definition of gamma function. So you can use this right here. So what is this actually? I think you can, from there you can get that this is actually nothing but this is gamma n by 2, right? Gamma n by 2. Okay, therefore this I to the power n is actually integration of d omega n minus 1, and then this part is actually half gamma n by 2. I think it's okay, there is no problem of that. Okay, now here you need to know actually a identity that I don't want to discuss that and how do I get that, but if we know this, then we can actually easily get this answer. So that this volume integral, that means if there is in such angle d omega n, then it is actually given by 2 pi to the power n plus 1 by 2 by gamma n plus 1 by 2. Okay, and therefore we just that means use this identity here, that means for this integration of this angular part, and if you use this, you can see that so this d omega n minus 1 is nothing but twice into pi to the power n by 2, right? And this will be gamma n by 2. Okay, I think you get this, right? Then because that means this is this is the standard integral that we are using. So to derive this that in this way, that means using this n-dimensional coordinate, we need to know a number of relations. Okay, and so if we use this now, what we get? We get 2 into pi to the power n by 2 gamma n by 2, and here it is half gamma n by 2, that is from the radial part, and that is from the angular part. Okay, and it is actually it is 2 cancelled, and then gamma is also cancelled. Okay, so it is actually pi n by 2. Now you get it, that I to the power n, that is actually pi n by 2. That's the thing, and you can easily now understand that what is I. I is nothing but the root pi. Okay, so this is the other way of other calculating this I, but here we use the concept of n-dimensional coordinate system. Okay, I hope you enjoyed it. Thank you.